Welcome to another important topic in TCP, that is TCP Congestion Control. What's actually congestion? When the load offered to any network is more than that it can handle, it is called actually congestion. Okay. So who will detect congestion in case of a network? Definitely the network layer, right? The network layer detects congestion when the queues grow large at routers and tries to manage it by dropping packets. Of course, if there is a number of packets which is more than that can be handled by different routers, what the routers will do, it will simply drop the packets, right? In such case, there is congestion. So it's up to the transport layer to receive congestion feedback from the network layer and slow down the rate of traffic that it is sending into the network. So who can control this traffic or who can control this congestion? Definitely the transport layer, because the ending machines only sending the data, right? Yeah, even if the network layer is detecting this congestion, it is up to the transport layer, because end-to-end communication is done by the transport layer. So the network layer will inform the transport layer that there is congestion, and this transport layer will inform the sender, yeah, please reduce the transmission rate because there is congestion in the network. So on the internet, TCP plays the main role in controlling congestion as well as main role in reliable transport. So what technique is used by TCP congestion control? The method used is called AIMD, Additive Increase Multiplicative Decrease, which is using a window and packet loss as a signal. So the main signal which indicates that there is congestion is packet loss. Whenever the routers are having more than that can handle, they will drop the packet, and the packet loss can be taken as a signal for congestion. So using a congestion window and this packet loss as a signal, transport layer or TCP can do the congestion control using this AIMD method. So TCP maintains a special window called congestion window, whose size is the number of bytes a sender may have in the network at any time. So depending on the network capacity, how many bytes it can send. Based on that, a congestion window will be set by the TCP at the sender side. Okay, congestion window is the number of bytes that can be sent. That definitely depends on the network capacity. And to TCP adjust the size of the window according to the AIMD rule. We will see what is actually AIMD and how this congestion window will be updated. So definitely for flow control, another window is maintained. Flow control means based on the receiver's capacity, how many bytes receiver can handle at any time. Based on that only the sender should send. Okay, and such a window is called receiver's window. That is maintained for providing a flow control. Flow control is actually used to maintain the flow without overwhelming the receiver. Okay, and congestion is mainly due to this network issue. So both should be considered in case of congestion. So congestion window is maintained, which is a number of bytes the sender may have in the network at any time. Within a network, how many bytes can be there? How many I can send now? That is congestion window. And flow control window is another one. Specify the number of bytes that the receiver can buffer, purely based on the receiver's capacity. How many I can send to the receiver? That purely depends on the receiver's buffer capacity. So both windows are tracked in parallel. To control the congestion, these two windows should be tracked in parallel, and the number of bytes that may be sent in the smaller of these two windows. Definitely to control flow and congestion simultaneously, the number of bytes sent or the actual window should be less or the smaller in these two windows. Okay. Just for example, suppose the receiver says send 64 kilobytes of data, because I am having such a buffer capacity. But the senders know that the burst of more than 32 KB clog the network. But the network is not having such a capacity. Sender knows that. In that case, sender will only send 32 KB without creating any congestion in the network. So that is first case. Receiver window is larger, but the network capacity is smaller. So network capacity based on the network capacity, the congestion window will be set. And the second case, If the receiver says send 64 kilobyte and the sender knows that burst of up to 128 kilobytes get through effortlessly. Network is having more capacity, it can hold 128 kilobytes, and receiver say that I am having only capacity of 64 kilobytes. What it will do, the sender will send only 64 without overwhelming the receiver. That is the example. Now coming to the TCP congestion control approach. The modern congestion control was added to the TCP by this Van Jacobson's contribution in 1988. Actually in 1986, as you know, internet became more and more popular, and that thing happened that is called congestion collapse, which is actually a prolonged period during which goodput dropped very steeply. Goodput in the sense, we know that communication involves both transmissions and retransmissions, right? Yeah, due to some errors or packet loss, there can be a lot of retransmissions also. Okay, the same data may have to be transmitted again and again. So throughput, we can say that the overall transmissions, the number of segments transmitted, whether it may be original data or its retransmission, together we can call it as throughput. And the goodput, actually the actual data segments, the useful information, how much it is actually transmitted without considering the retransmission, how much original data or how much useful information is got transferred over a unit or over a period of time. That is called goodput. So that was dropped very steeply due to congestion, more than a factor of 100 due to congestion in the network. To start, he observed that packet loss is a suitable signal of congestion. So how can the network or how can the transport layer can understand that there is congestion? Of course, using this packet loss. Definitely there are other reasons are there for packet loss, like error due to error or communication channel link error, like that, right? In wireless networks and all, definitely lot of packets may be lost. That is why we are adding this error control in the data link layer. Such errors will be masked by the data link layer itself. So transport layer, if you look into transport layer, we can say that the packet loss are signals of congestion in the network. So this signal, that is packet loss, comes a little late. Definitely after congestion only this packet loss will happen, right? So it is a bit late to understand that there is congestion. Only after packet loss we will understand there is congestion. Anyway, it's a very good signal to get an information about there is congestion. And the approach by Van Jacobson is that all the internet TCP algorithm assume that lost packets are caused by congestion alone. A good retransmission timer is needed to detect packet loss signals accurately and in a timely manner. So definitely a timer should be set up. Then only we can understand the packet loss, right? And the timer value should be properly adjusted. So within that timer expiry time, if there is no acknowledgement received by a sender, that means there is packet loss, and that is a clear signal for clear signal for congestion. And track the congestion window using sequence and acknowledgement numbers, and adjust the congestion window using AIMD rule. So initially we will set the congestion window, and using AIMD rule we will adjust the congestion window either to increase depending on the network capacity and receiver capacity, or decrease the congestion window based on the congestion signals and all. We will see how it is done actually. So we will call the algorithm here a slow start algorithm. The sender sends the initial window, maybe one segment. Sender may send just one segment, and the packet will take a round trip time to be acknowledged, right? Yeah, that packet from the sender will reach the receiver, and receiver will send back a reply back. So a round trip time will take to get a reply back from the receiver, right? Yeah. For each segment that is acknowledged before the retransmission timer goes off, the sender adds one segment's worth of bytes to the congestion window. That means for each segment received correctly and it's acknowledged before the timer goes off, it means that there is no issues in the network on the receiver. The sender will add one more segment to its congestion window. I can safely send one more segment within this time period. Like that, it will assume and it will add one more segment to the congestion window. Okay. So as we know, in case of congestion transport layer, each byte is actually separately addressed, right? That is why sender adds one segment's worth of bytes. Okay, and plus already one segment is sent, right? So that gap is also there. For that also one more segment will be added. So corresponding to one acknowledgement, one segment will be added. Corresponding to successfully send data, one another segment also will be added. So in effect, for every acknowledged segment, two more segments will be added to the congestion window. So congestion window is doubling every round trip time. Okay, and this algorithm is actually called slow start, even if it grows exponentially, right? In first round trip time, it will send one segment. In the second round trip time, it will send two. Third one, it will send four. Like that, for every segment, two separate segments will be sent. So it's doubling in every round trip time, and that is growth is exponential. Even then, we are calling it a slow start. So in the first round trip time, the sender injects one packet. In the second, it will send two, like that. You can see here, initially the congestion window size is just one packet, and a timer will be set here. That segment is received correctly. It will send a reply back. Now the timer is not yet expired, so it will set the congestion window as 2. It will send two segments, both will received successfully. So it will send 4 different segments. For each segment acknowledged, it will send 2 separate segments, right? Yeah, like that. It will send 4, then 8, like that. Now the issue with this slow start algorithm is that the slow start algorithm causes exponential growth. Eventually, it will send too many packets into the network too quickly, right? So when this happens, queues will build up in the network. Queues are full, one or more packets will be lost, and TCP sender will time out. Acknowledgement will be failed to arrive in time. So congestion is there is congestion in a sudden manner, right? So there should be some method to capture or seize this exponential growth somewhere without creating much problem in the network. And for that, we are using the slow start threshold. To keep the slow start under control, the sender keeps a threshold for the connection called slow start threshold. Initially, this value is set arbitrarily high. We don't know how many packets can be travel through the network without any congestion, right? So we'll set a high value initially, maybe to the size of the flow control window, receiver's capacity. And the TCP keeps increasing the congestion window in slow start until a timeout occurs. Okay, that is some packet loss happens, or the congestion window exceeds the threshold. Okay, in both cases, it will till that it will increase the congestion window size. So if a timeout occurs before the threshold happens, that means this threshold value is not safe, right? Yeah, before that timeout occurs, that means congestion will be there if we increase like this. So suddenly we have to do something. Otherwise, it's okay with this threshold, right? Yeah. So whenever a packet loss is detected, so before entering into the threshold, if there is a packet loss, that means this threshold value is beyond the network scope or network capacity, right? So we have to reduce. So whenever a packet loss is detected by a timeout, the slow start threshold is set to half of the congestion window, and the entire process will be restarted. So we have to reduce the threshold. How it will be reduced? To half of the current congestion window. So the idea here is that the current window is too large because it caused congestion previously, and that is now detected by a timeout, right? So earlier window size, that was half, right? Because this window size is increasing exponentially by doubling every round trip time. So just previously it was half of this, and it was safe. After that, maybe the timeout occurs. So half of the window which was used successfully at an earlier time is probably a better estimate for a congestion window. That is close to the path capacity but will not cause loss. So our aim is to maximize the network capacity, maximize the utilization of network capacity at the same time without congestion. That is why we are reducing it to half. And whenever the slow start threshold is crossed, TCP switches from slow start to additive increase. So when the threshold happens, that is the maximum limit is reached, then we should not again grow exponentially. After that, we will just switch into another mode that is called additive increase. What is additive increase actually? In this mode, the congestion window is increased by just one segment every round trip time. So you can see here in case of additive increase how it happens. Initially it was 1, after it received the corresponding acknowledgement it was 2, then 3, then 4. For every window, congestion window, just one segment will be added in the next round trip time. That is the additive increase. Now let us see an improvement over this additive increase multiplicative decrease algorithm using a heuristic. Okay, that is called fast retransmission. Let us see how this improvement can be done or what is a heuristic behind it. So there is a quick way for the sender to recognize that one of its packet has been lost. So far we have seen that the sender will understand about this packet loss only at the time of timeout, right? Yeah, when a sender send a packet and it receive no acknowledgement within the timer expiry time, it understands that its packet is lost. But even before that, the sender would be able to know about the packet loss. How that can be done? Yeah, that is using this acknowledgement itself. As packets beyond the lost packet arrive at the receiver, they trigger acknowledgement that return to the sender. Whenever the receiver receive anything, it will trigger back. It will give a feedback to the sender. Okay, so based on that, the sender can able to understand. We will see an example for that. Here we have a sender and the receiver. Sender send a set of frames, and suppose the last frame was x minus 1, sequence number is x minus 1. So receiver will definitely receive or send back the acknowledgement, right? What is the acknowledgement number? So if it receives x minus 1, it will send an acknowledgement x. That is, the next expecting sequence number is x. That's the meaning of the acknowledgement number, right? So the green colored ones are acknowledgement number and black colored ones are senders send sequence numbers. Okay, so after receiving x minus 1, receiver sent acknowledgement x. So sender sends x, right? But it is lost somewhere. It is not received by the receiver, so there is no feedback from the receiver. The sender is not aware of that. Only when the timer out or timer expires, it will understand, right? So the sender will continue sending the rest of the different segments based on the window here, right? How many segments remaining, based on that it will send. So x plus 1 will be sent, x plus 2 will be sent. These are correctly received at the receiver. So receiver will trigger back. It will send back an acknowledgement. But what will be the acknowledgement number for the next received one? Even though the received sequence number is x plus 1, the receiver will send an acknowledgement with sequence number x itself, because in order the correct expected sequence number is x, right? X is not yet received. So it will send a trigger, but the sequence number still will be x. For x plus 2 also it will send back acknowledgement with serial number x, acknowledgement number x. For x plus 3 also it will send x. So all these are actually duplicate acknowledgements, right? Yeah. So what the sender will understand? Yeah, receiver is receiving, but the acknowledgement numbers are duplicate, means yeah, in between something is lost. The remaining is received. So even before the timer for this segment x expires in sender will understand that the segment x is lost. So how to identify whether it is segment x or x plus 1? Based on the acknowledgement number, whatever is coming as a duplicate, that is the lost acknowledgement number, right? Yeah. So these acknowledgements bear the same acknowledgement number and they are called duplicate acknowledgements. So each time the sender receives a duplicate acknowledgement, it is likely that another packet has arrived at the receiver and the lost packet still has not shown up. That is why the same acknowledgement number is coming again and again. So this is an example. So, and the TCP arbitrarily assumes that 3 duplicate acknowledgements imply that a packet has been lost. So that is a heuristic taken. If 3 different consecutive duplicates acknowledgements are coming, it means his packet is lost. Okay, so taking this as a heuristic, even before the timer out, it can do for the congestion control. So this heuristic can be used to retransmit the lost segment before the timer expires. So that is called fast retransmission. And at the same time, it can be used to update the threshold. Our slow start threshold is there, right? We used to reduce it to half only when a timeout occurs. But here, even before that, we can reduce the threshold. So early congestion control can be done using this heuristic. So the slow start threshold is set to half of the current congestion window, just as with the timeout. Slow start can be restarted by setting the congestion window to 1 packet. And the version of this TCP with this fast retransmission, and that is called actually Tahoe. And the maximum segment size in case of Tahoe was 1 KB, and initially the congestion window was 64 KB. That is 64 different segments can be sent into the network. And but after that, due to some timeout and all, the threshold was set to 32 KB. And from there, first transmission or the segment 0 was transmitted. The congestion window grows exponentially, just like our slow start algorithm, until it hits threshold 32 KB. So at that point, when 32 KB is reached, what will happen? Yeah, we have to do additive increase, right? Yeah, after the threshold is passed, the window grows linearly. It increases by 1 segment every round trip time. And we can see this algorithm here with this picturization. Yeah, we start initially from in a slow start or exponential growth manner. Our threshold is actually 32 KB. Each segment is 1 KB. Okay, so in one round trip time, the first round trip time, only 1 segment will be sent. Next round trip time, 2 segment. Next one, 4 segments. Like that, exponentially it is growing. You can see here, when it reaches threshold 32 KB, that exponential growth will be stopped, then additive increase will be applied. Each round trip time, just 1 segment will be added. Okay, like this. And whenever a packet loss is detected, what will happen? Suddenly we have to stop these things. Packet loss means there is a congestion in the network. So drop that into or restart it from the earlier again. Okay, so we have to restart with the threshold should be half of the earlier congestion window. So the packet loss happen in around 40. That is segment or congestion window size was 40. Now it will be 20. Threshold is actually 20. Start from here again. 1, 2, 4, 16 like that. When it reaches this threshold, again additive increase will be applied like this. So this is the TCP version Tahoe. So the transmission is in round 13. One of them is loss in the network. This is detected when 3 duplicate acknowledgements arrive. Actually, this packet loss is detected not because of a timeout, but because of 3 duplicate arrives. Okay, that is actually fast retransmission. So thereby we can improve the congestion control method. Now one more improvement over this Tahoe, that is a fast recovery also. And the corresponding version of TCP is called TCP Reno. And how this improvement done here is TCP avoids slow start except when the connection is first started and when a timeout occurs. So only in these 2 cases slow start will be there. Initially only. Initially there will be definitely slow start. And when a timeout occurs also, this type of slow start will be there. Otherwise, no need of a restarting again using the slow start method. You will see that. Instead of repeated slow starts, the congestion window of a running connection follows a sawtooth pattern of additive increase and a multiplicative decrease. So this is exactly AMD rule. We will see that. You can see at the initial stage, definitely that should increase in a slow start manner. 1, 2, like that exponentially. It will increase until the threshold is reached. At the point of threshold, it will increase linearly. That is additive method. Additive. Whenever a packet loss is found out, if the packet loss is found out because of 3 duplicates. Okay, duplicate acknowledgement. In that case, there is no problem. Just reduce the threshold to half, and we have to start from that point a fast recovery. That is again additive increase method will be applied. From there, add one more in every round trip time like this. Again, other packet losses found. Stop this additive increment. Go to the threshold. Reset the threshold to half of the current congestion window. Start from there, additive increasement. So a sawtooth form will be there. So in between, only if there is a timeout, the slow start will be repeated. Otherwise, this sawtooth pattern will be there. So we can have a fast recovery. So normally in the previous case, in the Tahoe case, what happens here, when a packet loss is found, it will restart from this point, come here, again start from 1, 2 like that, right? But here the recovery is fast, not going to the 0 or the minimum version of congestion window, but to the threshold, right? The reset threshold, that is half of the current congestion window. From there we can start linearly. That is fast recovery. And the corresponding version of this TCP is called TCP Reno. So these are the different improvements over the TCP congestion.